Hello, in this video, we're going to discuss the concept of elasticity. Uh, you are familiar with elasticity because you played around with the rubber bands. You know, rubber bands, you pull them out and then they go back to the original length, right? Springs are also another example of elasticity where you pull spring out and then you let go and the spring goes back. You may not be familiar with wires being elastic, but you can actually do this experiment on, say, steel wire or nylon wire. Almost every object is actually elastic. If you deform it a little bit, and when whatever you pushed or constrain it for deforming, if you let go of that, it tends to come back. Not everything will do it, but if it's elastic, it will come back. Okay. Some things are more elastic, so you can deform them considerably, and some are really not that elastic, right? And if you deform just a little bit, it will break. Well, let's look at a hypothetical experiment. Suppose you take a steel wire of some length L0, and you start to somewhere here you tie it very rigidly, so we are sure it's very stable. So this is where it's totally tied. So if you pull on it, this will not break over there, say, ideally. Okay, so when I hang some block, its weight will pull on it, and you will see that the length becomes bigger. So the amount by which it gets bigger is proportional to how much weight you put in. Kind of makes sense, right? If you look at this is static equilibriums, and if you think of this wire as a system, kind of like a spring, then basically the wire is being pulled on both directions by this F. You might say the wire is also pulling back. Wire is also pulling back, pulling this guy back with F, pulling on the support with F. So those are forces by wire, and this is the forces on the wire. So this we say we're going to talk more technically a little bit. There is a stress that developed inside the wire. Like you have an example like a tension in the string. So it's the same type of thing. So now we look at the tension that developed versus how much I stretched. So I have a particular length wire that I'm working with. Okay, say I'm working with 1 meter wire. I'm just looking at how much is developed. You might use this as millimeters and things like that. So as I put more and more, I make the force on the wire more and more. Initially, it's kind of linear, and then it becomes non-linear. Meaning, like if I put double the force, I get double the extension in the linear. But here, I double the force, but I don't get double the stretch. Actually, get much less the stretch. Somehow, it's got to the point where it's not responding as well. Okay, and then there comes a region where actually, if I extend that, it becomes deformed. It doesn't want to come back. So all the way here, if I go all the way this amount of extension up to here, the wire goes back. But over here, the relationship is very simple. And over here, this is nonlinear. I have to actually do the experiment to figure out what the nonlinear relationship is. But here, it's linear, and I can well characterize it with a slope of this line. Okay. And over here, it comes back. So this is all elastic. We say this region is the elastic region. Over here, when I go over there, it actually deforms permanently. you might have played with a spring, the pull, and then eventually let go. It's not going back. It just maybe goes partway. That's it. Same thing happens with a wire. If you pull beyond certain elastic limit, it just gets longer. It doesn't go back to the original length. All right. So that's called plastic region. And at the end of the plastic region is a point where you pull so that it actually broke somewhere. Wherever the weakest link was, it broke. So that's called breaking point. All right. All right, so we can define that to be the maximum force you can apply and the maximum length that you can extend for that wire. It turns out we can write some relationship. So this experiment says that how much I get, let's look at just this part, the linear part. We're only going to get linear part. So we're going to just look at this part of the graph, which the extension that I get depends on how much force was applied. But also, you know, if you have 1 meter wire, you might get, say, 1 centimeter. Now you take same material and you have 2 meter wire, you're going to get 2 centimeters. So how much you get also depends on how long a wire you got. So we kind of divide out by, so the divide by L, so we get rid of this, like, you know, I want to know how the material is behaving, not how long I have. So I want to have some better characteristic, and the better characteristic is the fractional change, and that thing is called strain in the materials. This is the strain or linear strain, because we are talking about length changing. You can imagine volume changing, that you're probably very familiar. You take a balloon and you can just squeeze it and make it less volume, right? So same thing you can do with a block of steel. You can actually compress it and you can change the volume. So there will be strain associated with this volume change as well. So whatever change I'm looking at, if I look at a fractional change, we call it strain, or different types of strain. We may talk later, okay? And we will use the letter epsilon to denote strain, okay? All right, so let's do you might say, you know what, it depends on length. How about if I have very thick wire, apply the same force, do I get the same strain? Answer is no. It actually, so if I do a same, say, steel, I take the same steel, I make two thickness wires, say thickness A1, this area of cross section A1 and area of cross section A2. This is thicker wire. So if I want to deform by a particular strain, of course thinner wire will require less force, right? And then thicker wire. So this is the thickness is playing also a role. So it's not the force, but thickness is also playing a role. And I don't want to just study every single thickness material, right? I want to know how steel will behave, how concrete will behave. So we go and figure out if it's possible to construct a quantity by dividing the area out. So if I divide the area out and then plot this quantity versus the strain, guess what? These 2 points, for the same strain, I was getting 2 different forces, but if I do divide by area, if it lands on the same point, that means dividing the area actually remove the sample dependence, the particular thickness dependence, particular length dependence, right? The length dependence got rid of that, but thickness dependence I got rid of that. So instead of focusing on force, it will be if I focus on this force over area, I will capture the essentials the material property of steel itself, which will be different than of rubber. And so this is straight line equation, right? So if you don't have any force, there is no extension. As you increase force over area, then the strain changes linearly. This linear relationship between these two is called Hooke's law. This is called stress. Force over area is called stress, and we use a symbol sigma, letter sigma, small letter sigma to denote this, and we use small letter epsilon to denote this quantity. So want to write down Hooke's law for you? Hooke's law is experimental observation that I have here written down in math. So here is a stress and here is a strain, and the only thing, because it goes to the origin, the only thing left in this straight line is the slope, and slope is the constant of proportionality between stress and strain. Y is called Young's modulus. And it will vary over a very large range depending on how easy it is to, stretch something or shrink something. How easy it is to change its length, whether to shrink it or to stretch it. In the wire, we usually do the stretching, but some other places you may have a shrinking of the length. For instance, if you have a steel, suppose you have some steel and which is sitting on a very concrete surface, and you loading this up, then you may be interested in the change or shrinking of this. But it will be same Young's modulus that will be used for this steel. Sometimes material may behave shrinking differently than extending, right? So there may be two modulus. One modulus for extension and one modulus for compression. So you may want to you may encounter those examples later. When it's extension, when you are stretching is extension, then you call it tensile. And of course, when you are shrinking it, then you call compression. And they may be listed as that in table. We would not be using all this detail, but you should know about that, because when you look up the table, we will be using just Young's modulus given to us in problems. So take care. Bye.